Before we get started, there's two things I'd like to mention. The first is that all the slides, speakers, notes, and demos are available for download, and I'm going to be providing a link at the end of the talk. I tend to be one of those folks who can't keep up with the speaker and take notes at the same time. So for those folks who are in the same situation, there's no need to take notes. Everything I'm covering is going to be available for download. Second is to please hold all questions until the end. If you've got questions, make a note of them, and then ask me after the talk. And with luck, I'll be able to answer most of your questions during the talk itself. So, in the beginning, which for this discussion is 1984, there was the Macintosh file system, otherwise known as MFS. So this file system was introduced with the original Macintosh computer in January 1984, and it was designed to store files on 400 kilobyte floppy disks. So MFS had a number of features that would be familiar to later Macintosh users. Used resource forks, also had a lot of things stored in the resource fork to simplify application delivery, especially if you wanted to ship your application to more than one nation. And it also supported the graphical user interface that the Mac was using in place of other operating systems' command line interface. So one feature that was different from how Mac file systems work today is that MFS did not support the concept of a hierarchy of directories. Instead, MFS was a flat file system where all the files were actually stored at the same level. So folders existed as a concept in MFS, but they worked completely differently from the way that they do on modern file systems. The Finder created the illusion of folders that were visible in the Finder, but then when you went into your application and opened the open and save dialog boxes, you didn't see the folders. There was always a folder named empty folder that could be used to create new folders in the Finder by altering the existing empty folder. And as folders were altered by adding files to them or by renaming the directory, a new empty folder would then appear. So in reality, what the file system was doing was it was storing all files using a directory and file handle pairing. And when you went to display the contents of a particular folder, what was happening in the background was that MFS would scan the directory for all files that matched that handle, and then it would display the contents of that search. So MFS had some limitations. Maximum volume size was 20 megabytes. Megabytes are close to, but not exactly megabytes. Maximum file size was also 20 megabytes. Maximum number of files was an enormous 4,094. And maximum file name length was 255, although the Finder imposed a limitation of 63 characters for a file name. So you supported 255, you really only got 63. So MFS was discontinued as the Mac's primary file system by Apple in September 1985. Reading and writing to MFS volumes continued to be supported up until System 761, when Apple dropped support for writing to MFS volumes. And all support for MFS was dropped in macOS 8.0 and later, and there was never native support for it on OS X or later. Now, that said, one of Apple's provided example file system plugins for OS X is named MFS Lives, and it provides read-only support for MFS volumes. So for those of you in the audience with that one really old floppy, there's hope. So why was MFS replaced? Well, this was a neat case of hardware needs driving software design, and to replace MFS, Apple introduced Hierarchical File System, otherwise known as HFS, in September 1985. And the reason why it was introduced was to support Apple's very first hard disk drive for the Macintosh, the hard disk 20. So the reason for the change is that MFS had been optimized to be used on very small and slow media, namely floppy disks. So in contrast, the hard disk 20 contained a 20 megabyte hard drive, this enormous amount of storage for the time, and that provided over 50 times the data storage of the stock 400 kilobyte disk drive. So the introduction of larger media like the hard disk 20 exposed a scaling issue in MFS that Apple needed to address. MFS's method of displaying files in a folder by searching for directory and file handle pairing worked well when you were working on a very small scale of hundreds of files and kilobytes of storage, but it had a noticeable performance impact when you were now dealing with megabytes of storage and thousands of files. So Apple's solution to this problem was to replace MFS's flat file structure with the directory-based file system that leveraged a new file known as the catalog file. So the catalog file incorporated a binary search tree structure, also known as a B tree, that could be searched quickly regardless of the size of the storage volume. So this is how Apple's handling MFS's search impact. So HFS incorporated a number of features first introduced in MFS, including the use of resource forks, and also having a maximum file name length of 255 characters, although now the Finder is imposing a further limitation saying you can't use more than 31 characters in any particular file name. So this is shorter than MFS's 63 characters, but this is still a Finder limitation. It's not from the file system. And HFS also introduced new features, including actual directories stored in a hierarchy. Files were also now referenced by the file system with unique file identifiers rather than by the file names. And this allowed files to be named almost anything without losing track of which application was going to be able to open them. And the designers of HFS also redeveloped various file system structures in order to be able to handle these larger numbers, this greater storage. So most were upgraded from MFS's 16-bit integer to now being 32-bit. However, there was one place where upsizing did not take place, and that was in the number of files supported. This remained a 16-bit integer, with HFS being able to support up to 65,535 files, and this becomes important later. So as mentioned, HFS had some limitations. Maximum volume size was 2 terabytes, though to be honest, back in the HFS days, I couldn't imagine having a 2 terabyte size drive. Maximum file size was 2 gigabytes. I did run into that one. Maximum number of files, as I mentioned, is 65,535. Maximum file name length remains 255, though the Finder is still saying no more than 31 characters. So along with solving MFS's issues, HFS had a few of its own. Though the catalog issue file, which was the replacement for MFS's directory file handle pairing, stores all the files and directory records into a single data structure. So this can result in performance problems when you're multitasking, because now only one program at a time can write to this structure. So if an application is hogging the system, that means now other applications are queuing up and waiting for their turn to write to the catalog file. And that's certainly when you would see the stopwatch pop up and you'd just go, man, this is taking forever. Also, damage to the catalog file could result in catastrophic file system damage because this was the only place where all your file and directory records are stored. So if this got hosed, now you had a big problem. And another issue with HFS had to do with block allocation. So a storage volume is inherently divided into logical blocks of 512 bytes. HFS groups these logical blocks into allocation blocks, which can contain one or more logical blocks depending on the size of the total size of the volume. HFS uses a 16-bit value to address these allocation blocks, and that limits the number of allocation blocks to 65,535. So, because HFS could support a maximum number of 65,535 files, with each file being assigned at least one allocation block, regardless of the size of the storage volume, this introduced as a logical consequence, you have a minimum file size limit, so that any file could not be smaller than one allocation block or 165,535th of the size of the drive. So when available drives were well under 1 gigabyte in size, this wasn't really a big issue. But as drives got larger, the smallest amount of space that any file could occupy became excessively large. So to illustrate the issue, let's take a look at how HFS operates on a 1 gigabyte drive, which seems laughably small today. So 1 gigabyte divided by 65,000 comes out to around 16 kilobytes. And in fact, the Finder rounds it up to make it 17. So that meant that the minimum file size of any file on a 1 gigabyte drive was effectively 16 kilobytes, regardless of the file's actual size. So that meant even a 1-byte file would take up a minimum of 16 kilobytes of disk space. So for users with a lot of small files, this meant that a lot of disk space could just be lost to this minimum file size limitation. So to fix this storage allocation and to add other improvements, Apple introduced yet another file system in 1998. So Apple introduces the HFS Plus file system in 1998, which is the one that we use today, and it was designed to fix the block allocation issue in HFS. So this was accomplished by upgrading block allocation to now use 32-bit integers in place of HFS's 16-bit, and that allowed for a much lower minimum file size. We still have it around, but it's much more manageable today. So along with the block allocation issue, a number of other issues were addressed as part of creating HFS Plus, and this included implementing Unicode support and also addressing the issue of long file names. So you can now actually use 255 characters in a file name. And over the years, Apple has added some new features to HFS Plus. And HFS Plus is not only used on Macs up until very recently this year. iOS, tvOS, and watchOS were also using it, with HFS Plus being extended on those platforms to add support for per-file encryption. We're using FileVault 2 on iOS, tvOS, and watchOS. They went another direction. So HFS Plus first shipped in 1998. That's 19 years ago. Since then, file systems and other platforms have shipped that include features that are not present in HFS Plus. Among the issues are, when it comes to data checksumming, HFS Plus does not include the ability to checksum metadata. This helps to detect file corruption, so it's a nice feature to have. When it comes to tracking reads and writes to the file system, HFS Plus has 1 second granularity, and that means that reads and writes to the file system can only be tracked down to the second. Other file systems are able to track down to the nanosecond, which means that they're much more able to catch partial reads and writes and deal with them before they can cause problems for the user. Also, concurrent access to the file system. This is an issue that carries over from HFS. HFS Plus is a single-threaded file system, and that means that only one process can be updating the file system at any one time. So again, if an application is hogging the system, that means that other applications are now waiting their turn to write to the file system. And frankly, this particular issue may be most visible during time machine backups. And this is actually one place where SSDs really helped out a lot, because even though it's a single-threaded file system, SSDs have so much better performance that the reads and writes can simply just be processed that much faster. So other limitations include date limitations. HFS Plus stores dates in 32-bit integers containing the number of seconds since midnight, January 1st, 1904 at Greenwich Mean Time. And that consequence is that HFS Plus's maximum representable date is February 6, 2040 at 6:28 and 15 seconds Greenwich Mean Time. Now, back in 1998, they probably didn't think this was going to be too big of a problem. It's 2017 now. We should probably address this. Sparse file support. HFS Plus does not support sparse files, which are a type of computer file that attempt to use file system space more efficiently by writing reference metadata for the empty space in files. So file systems that support sparse files can simply say, okay, basically from this sector to this sector, it's all empty space. We're not going to write just zeros to everything. We're just going to say, basically from here to here, it's empty. Makes for a much smaller file. What HFS Plus does, it goes, okay, so it's empty from here to here. Let's just write a bunch of zeros. Not as efficient. HFS Plus also does not support capturing file system snapshots, which means creating a read-only copy of the state that the file system was in at a specified point in time. And another legacy issue is, frankly, that HFS Plus was not designed for use with Intel processors. In 1998, we had Motorola processors. We had PowerPC processors. These were big endian processors. And the reason why this matters is that Intel processors are little endian processors. Big endian and little endian expect to have data fed into them in a particular way, and they happen to be completely opposite from each other. So when you're reading metadata from an HFS Plus drive, in order for an Intel processor to understand it, it has to be byte swapped before the processor can understand it. Now, there is a negligible performance impact for it, but this is something that has to be accommodated for with HFS Plus, that other file systems simply don't have this issue. So with HFS Plus showing its age and its legacy roots, Apple has made the judgment that continuing to maintain and evolve this 19-year-old file system is no longer tenable. Apple needs a new file system, and Apple File System is being born from that need. So APFS includes a number of features that are not currently available in HFS Plus. One is they've upgraded block allocation to now use 64-bit integers. And that means that APFS can support over 9 quintillion files on a single APFS volume. And this is in place of HFS Plus's 4 billion and change on a single volume. Also, APFS does support nanosecond timestamp granularity. This improves on HFS Plus's 1 second timestamp granularity. APFS does support the use of sparse files that allows APFS to handle empty space much more efficiently. Snapshot support. APFS does include support for capturing those file system snapshots. And those snapshots are also able to be mounted as read-only volumes using the mount APFS command, and I'll be going into that in a little bit. Also, working with the timestamp granularity, Apple offers a new capability with APFS called Atomic Save. And this capability performs saves in a single transaction that, from the user's perspective, they either succeed or it didn't happen at all. And this means that partial writes to the file system don't occur. And the reason why this is important is that a partial write to the file system may cause more trouble than that write not happening at all. So this is definitely an improvement for us. Also, extended attribute support. Both APFS and HFS Plus do include extended attribute support, but APFS is having this support built in natively, where HFS Plus had to have it retrofitted in. So APFS is structured as shown, with containers being the base storage unit of APFS. Containers are pools of storage which are conceptually similar to core storage's logical volume groups. And in turn, the containers host APFS volumes, which are your actual mountable file systems. Each volume then generally maps to a matching namespace, which Apple is defining in this case as meaning sets of files and directories. So this is the stuff you're actually storing on the APFS volume. So while full support for managing APFS is not available at this time in Sierra, it is possible to create containers, volumes, and namespaces using distkutil. So let's take a look at how this works, beginning with formatting a disk to use APFS and set up one container. So first thing we're going to do, let's go ahead and run distkutil list, and I've got an unformatted drive available. So let me just grab that identifier, disk0, and what I'm going to do is run distkutil, partition disk, plug in the disk identifier, which is dev-disk0. I'm going to say that I just want one partition on it. I want GPT for the partition table. I'm going to format it as APFS. I'm going to name the drive APFS, and that I want to use 100% of the drive for that. All right, let's go ahead. Goes through, sets it up, and now I have my new APFS formatted drive sitting out on my desktop. Now to do further work with APFS volumes, you'll need to use distkutil's new APFS functions in Sierra and later. So to list available APFS objects, including containers and volumes, you would use distkutil APFS list. So Apple never wants you to forget in Sierra that APFS is still a work in progress. So anytime you run distkutil APFS commands, you will see this warning. And Apple recognized that folks would likely want to skip this message if possible, so they included a command line option for bypassing it. However, this bypass option also makes perfectly clear Apple's guidance with regards to storing your data on APFS volumes at this time in Sierra. So once you're past the APFS warning, the output of distkutil APFS list should look similar to this. So in this case, there's one APFS container and one APFS volume present on this Mac. So if you have an existing APFS formatted drive and you want to add additional containers to it, you can use the create container command. And this command will also convert an HFS Plus drive to APFS and set up an empty container. So let's take a look at how that works. So first thing, let's run distkutil list, because we want to grab the identifier of our HFS Plus volume over there, which is disk0s2. And we're going to go ahead and run distkutil APFS create container. And we're going to specify that we want to run this on dev disk0s2. All right. Everything looks good. Let's go ahead and hit return. Get our lovely warning. We're going to say yes. Goes through, creates our container. And next thing we're going to do is run distkutil APFS list to make sure it worked. Get our warning, say yes. And yes, our HFS Plus drive has disappeared and has now been converted to an APFS formatted drive with our container. However, if you notice, nothing is appearing on the desktop. And that is because our container is not our file system. APFS volumes are our file system. So right now, we have an empty pool of storage, but nothing's going to mount in it until we actually add a volume to it. So to destroy an existing APFS container and all the volumes and namespaces on it, you can use the delete container command. So the APFS volumes are unmounted, and all APFS volumes are deleted along with their parent container. So in Sierra, the APFS container's former physical disk will be reformatted as HFS Plus as part of the process, and you can optionally specify a name for the HFS Plus volume. So if no name is chosen, it'll just default to naming it Untitled. So let's take a look at how this works. So first thing, let's go ahead and run distkutil APFS list, get our warning, and let me grab the identifier for my disk, which is disk1s2, and I'm going to run distkutil APFS delete container, specify that I want to use disk1s2. You can also use dev disk1s2, I just put in the identifier by itself. And I'm going to specify that the new drive is just going to be named new HFS Plus when it gets reformatted. Go ahead, hit return, get our warning. Goes through, destroys everything on that APFS container, destroys everything, reformats it as HFS Plus. And now we're back to it being an HFS Plus drive. So to grow a container, you would use the resize container command. And this allows the option of growing a container's available allocated space when more physical drive space is available, like say you have a RAID or you're using this in a VM or something else. So if you want to have your container resized to fill all available space, you would use the number 0 for the size. So first things first, let's go ahead and run distkutil list. And I have a drive that has 64 gigs of space available on it, and I have another drive, I have my APFS container that's using 42.7 gigs of space on it. So let's go ahead and run diskutil APFS list because I want to grab the identifier for that container. Okay, that's disk1s2. So let's go ahead and, let's go ahead and get that for copying. Next, we're going to run diskutil APFS, resize container, pop in that identifier, dev disk1s2, and I'm going to say 0 because I want to use all the available space. Get our lovely warning again, say yes. Now it goes through, resizes, and now my APFS container now has access to all the available space on the drive, which is about 64 gigs. Now, if you have an existing container and you want to add volumes to it, you can use the add volume command. So for here, let's go ahead and run diskutil APFS list. Get past the warning. I'll be so glad when this warning goes away. So I have my container, that's disk1s2, and I just want to add a volume to it. So I'm going to go ahead and run diskutil APFS add volume. And I already have a volume in there called APFS, so I just want to add a new one. Just call it new APFS, and I'm also specifying that it has to be formatted as APFS. I guess you could put an HFS Plus volume in there. I'm not sure how that would work. Say yes, and now out of my desktop I have a new file system popping up. That's new APFS. Now the create verb is a convenient command that combines the functions of the create container and add volume verbs. So this will convert an existing HFS Plus drive to an empty APFS drive with an empty container, and then it'll set up one APFS volume in the container. So this is conceptually similar to the partition disk command I ran a little bit ago. So I'm going to go ahead and run diskutil list, get the identifier for our HFS Plus drive, which is disk0s2 in this case. And then I'm going to go ahead and run diskutil APFS create, and specify that I want to do it to dev disk0s2, and then I want to name the drive APFS. So say yes to the warning, goes through, HFS Plus goes away, it's now been replaced by APFS, and let's just double check to make sure that everything worked right. So we're going to run diskutil APFS list, get our warning again, and sure enough, there we are, we've got our container, and we've got our one volume showing up. So something to be aware of is that volumes hosted in the same container will all display the same size and available free space of their parent APFS container. So this behavior is referenced when you list the available APFS volumes, and you look for the drives that are listed as space sharing. So let's take a look at how this works in practice. So I've got two APFS volumes mounted on my desktop, and I'm going to put a 10 gigabyte file on one of them, and I'll just name it 10 gig file. All right, put in my password for sudo. And I've got 10 gig file appearing over here, nothing over here. But if we run a disk space check, both are going to show up as having 10 gigs used. And the reason is that they're both coming from the same container. The container knows I have 10 gigs used on one of my volumes. So I'm going to take it away from not only the volume it's used on, I'm also going to make the other one show that it's got 10 gigs used, even though there's nothing appearing on that other volume. The container is managing all of this, and it is able to do it intelligently for you in the background. So because the free space is being managed at the container level, you shouldn't run into an issue where someone tries to save too much space to an APFS volume. But this behavior is something to be aware of when you get asked why someone's two drives apparently have X gigabytes of free space each, but they can only save a total of 10 of X gigabytes onto both drives. So to help with this issue and to save on disk space overall, Apple is also introducing a new way to handle duplicate files as part of APFS. So this is kind of cool. So I've got an APFS formatted drive here, and I've got an HFS Plus drive formatted here. And they both have 10 gig file on them, and I'm just going to duplicate it. So first of all, let me go over to the HFS Plus drive, get that copy going. All right, that's going a good clip. You know, that's pretty speedy. And I'm going to come over here to APFS, and yeah, it's done. Do 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 do. You know, maybe we should, you know, take this time to go to the bathroom, get some coffee. You know, this is going to take a while. You know, this copy job, and oh, just finish already. Oh, thank God, it's all done. All right, but if we go and take a look at this copy on our APFS drive, it's also showing up as a 10 gig file. How is this possible? How does this work? It copied so fast. Well, Apple calls this new copy behavior cloning, and it's defining a clone in the APFS context as being a copy of a file directory that occupies no additional space for file data and can be created almost instantaneously. So when a cloned file is modified, only those modified blocks are being written to disk. And this allows the file system to do a couple things. One, store multiple revisions of the same document by tracking which blocks were used, and also just use less file space overall by only tracking those changes to the disk and using the original file as a reference for the modifications. Now, the question that I'm sure just occurred to a bunch of people is, what happens if you toss that original file? And the answer is nothing. The file system is like, oh, okay, I'll just keep track of these blocks. Even though that original file is gone, I'll just keep reassigning it as needed until all copies of that file are gone. And at that point, it can say, okay, those blocks are free. I can now allocate them to be used by something else. But until that time, it just handles it for you silently, in the background, automatically, just does it for you. You don't have to worry about this. So as mentioned previously, APFS includes the ability to create snapshots of the APFS file system. And for those not familiar with this, a snapshot is a read-only instance of a file system on a volume. So snapshots can be used to make backups work more efficiently and also offer a way to revert changes to a given point in time. So in the APFS developer preview included with current releases of Sierra, and that's all I'm covering today. I'm not going to speculate about the future, which is coming in like half an hour. The APFS snapshot utility can be used to create, delete, and list snapshots. And Apple also noted in its APFS documentation before this particular section went away that the APFS snapshot utility will be disabled in a future release of macOS. So this tool is going to be replaced by another snapshot tool at some point. So to create a new snapshot on an APFS volume on Sierra, you would run the command shown on the screen with root privileges. And let's take a look at how this works. So we're going to go ahead and run sudo APFS snapshot. We're going to use the -c flag to say that we want to create one. We're going to name the snapshot as just new snapshot, excuse me, and we're going to store it on volumes APFS. That's the drive it's going to be associated with. All right, put in our password. Here we get a completely different warning that also says basically, don't trust this. This is pre-release software. I just thought it was interesting Apple decided to put in a completely separate and different warning for this particular tool. To list the available snapshots in an APFS volume on Sierra, you would run the command shown on the screen with root privileges. So in this case, we've already created a snapshot. We want to take a look at where it is. So we're going to run sudo APFS snapshot. We're going to say -l, and we're going to ask it to list the snapshots associated with volumes APFS. Put in our password for sudo. And we get our warning again, but underneath that, we get this listing for new snapshot to show that we do have a snapshot associated on this drive. And to delete a snapshot on an APFS volume on Sierra, you would run the command shown on the screen with root privileges. So we're going to go ahead and run sudo APFS snapshot -d, and we're going to specify that we want to delete new snapshot from volumes APFS. All right, put in our password for sudo. And just to make sure that it is gone, we're going to go ahead and run sudo APFS snapshot -l. For volumes APFS. And sure enough, here we get our warning, but now there's no listing underneath the warning. Now, to mount an existing snapshot as a read-only volume, you'll need to use the mount APFS command and using its -s option. So as part of using the command, In Sierra, you'll also need to specify a directory for the snapshot to mount to. Hopefully this is not something we'll have to do in macOS Next, whatever it is, but you do have to do it with the developer preview in Sierra. So you can also see more information about it. Once the drive is mounted, you can see it as a read-only drive in the Finder, and you can also find out information about how the snapshot is mounted by using the mount command. So let's take a look at how this works. So first thing, I'm going to set up a 10 gigabyte file, just call it 10 gig file, and store it on volumes APFS. All right, there's my file. Now, because I'm a cautious sort, I'm going to go ahead and create a snapshot of this drive. So I'm going to run sudo APFS snapshot-c. I'm going to just call it 10 gig snap and associate that with volumes APFS. All right, life is good. Oh, and here I make the mistake, the terrible error. No, don't do it again. Not again, not the nightmares, no! Oh, I'm such a fool. I have a snapshot. So what's the first thing I need to do? I need to put up a mount point. So I'm going to create a desktop folder called recovery. You could name it anything and put it anywhere. I'm just happening to put it on the desktop. Okay, so there's my directory called recovery. And the next thing I want to do is I want to mount that snapshot. So I'm going to run mount APFS. I'm going to use the -s option to indicate that I'm using a snapshot. I'm going to say that I want to use 10 gig snap from volumes APFS, and then I'm going to be using desktop recovery as my mount point. All right, here's hoping. All right, there I've got my snapshot mounting as a read-only volume, and let's go take a look at it. Please, 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 please. Oh, thank goodness, 10 gig file is there. I'm saved. Also, because bad things can happen to good drives, if you want to fix a malfunctioning APFS drive, you can run the fsic APFS command with root privileges. So let's just take a quick look at how that works. So we'll run disk-util list to grab our identifier, which in this case is disk1s2. And now I'm just going to run sudo fsic APFS, plug in our identifier, which is dev disk1s2, put in our password for sudo. Sure enough, everything looks fine. Now, one area that was affected by this is that Sierra's OS installer fails right away when you try to install it onto an APFS formatted drive. And the reason for this failure is that it's running a disk check. And it fails pretty hard when you try to run it against an APFS formatted drive. And when the disk check fails, the installation process hard fails. So can you install 10.12.5 onto an APFS formatted drive? Not right now. So as Michael mentioned, one of the things that Apple's been promising as part of the move from HFS Plus to APFS is a smooth conversion process. The tool that Apple will be using for the conversion is called APFS HFS Convert. It is available in Sierra. I've tested the conversion process in Sierra, and it works as long as the conditions shown on the screen apply. So these rules may not apply to the conversion process in future OSs. This is just for Sierra. That's all I'm going to be talking about. No speculation about the future here. And to run the conversion process, you first have to make sure that all the conversion conditions that I mentioned on the slide before have been met. Once they have been, you would run the command shown on the screen with root privileges. So let's take a look at how this works. So disk-util list, and grabbing my disk identifier there. And next thing I want to do is run disk-util unmount, because the drive must be unmounted. And I'm going to say volumes HFS to APFS, so that's now unmounted. And next thing I want to do is just run sudo APFS HFS Convert and plug in the identifier. Oh, sorry. Also plug in -v just to make sure it's verbose, and then plug in my disk identifier. And this drive is empty, so this conversion is actually going to take not too long to complete. So put in my password, I get my warning, say yes, and now it's done. Like I said, this is an empty drive. It converted really fast. And now I'm going to go ahead and run disttil, APFS disttil list. And sure enough, my drive is now showing up as APFS with my disk identifier shown there. And if I run disttil mount, it'll mount the drive. And if I run disttil APFS list, it shows that everything is normal. So at this point, the drive's been converted. Life is good. So when I've tested converting encrypted drives in Sierra, I frankly get results that look like this. The conversion process fails with an error. The drive winds up in a state that disk utility labels as uninitialized, and it's not possible to mount the drive. It's a total loss. When I've tested converting Fusion drives in Sierra, I get results that look like this. APFS HFS convert gives me a message that I targeted core storage logical volume, and the process halts at that point, and no conversion takes place. And I think that's largely because I can't fully unmount the drive. It's always going to show up as being a core storage volume. So there's currently several limitations of APFS to be aware of that may only apply for the next maybe 20 minutes or so. Startup disk is that an APFS volume cannot currently be used as a startup disk in Sierra. I know some folks have managed to get it to work. It takes some jiggery pokery, but by and large, I'm going to stick with my rule of it can't be used as a startup disk. Case sensitivity, volumes can only currently be case sensitive. This is the reverse of how it is on HFS Plus, where the default is to a case insensitive volume. Time machine backups are not currently supported with APFS. I suspect that Apple is going to be doing some substantial reworking of Time Machine to incorporate snapshots. Also, for the last two, core storage is staying behind on HFS Plus. It is not moving over to APFS. So File Vault 2, that relies on core storage. That is going to be replaced by APFS's native encryption scheme, which we will hopefully learn a lot more about over the course of this week. Also Fusion drives also rely on core storage, so they currently just don't work on APFS at all. And because you can never have too much information about something that is new, I've got some useful links. More useful links. And potentially the most useful link you see in this entire presentation. This is how you get it all. Top link gives you a PDF of all the slides and speakers notes. Keynote slides are available from the link below, and that gives you everything. Everything I've been talking about, all my speakers notes, all the demos, everything. So I'm going to leave that up on the screen. And how are we doing on time?
We'll post it in the Slack.
I'll also post it in the Slack.
Yeah.
There'll also be a blog post on it.
Everybody, round of applause for Rich Trouton.